Okay, now let's just very briefly go over the material condition. So first off is RFS. Now these are material conditions. These are all for things that have a volume, okay? Like holes or pegs or whatever. These are all going to have a volume. Whether it's a volume that is empty or a volume that is filled. Now, if you don't see a symbol, so you have your feature control frame right here, and it says it's perpendicular, and you see 0.05, and there's nothing next to it, well, then that is assumed to be meaning regardless of feature size. Regardless of feature size means that nothing matters. It doesn't change. Like if it's bigger, if it's smaller, the tolerance zone is the tolerance zone. We don't get any extra, we don't get any less. It's just 0.05. So it does not matter what's going on there. Now, if we have the maximum material condition next to our tolerance, okay, right here, let's do this again. And I'm going to say, actually, I'm going to do position tolerance. I like that a lot better. Sorry about that, drop my pen. There we go. And I'm going to say 0.05, and this time maximum material condition. That will go right next to that number. And of course, I would have some datums off here. Now, what this says is saying, well, okay, for one, my part has some sort of size. Let's say it's a peg like this. And there is only so big it can be. It's going to have a diameter, which maybe it's going to be 0.5. It can't be bigger than that. It's got to be within this. However, as this peg gets smaller, obviously if it's trying to fit into a slot somewhere, the smaller the peg, the easier it is for it to fit in there. And so it can move back and forth more. What this symbol tells me is that as I move away from this flap, maybe I go from 0.5 to 0.4, I get extra tolerance. I'm able to use that tolerance and say, well, I can move back and forth more. Now, if that doesn't make 100% sense now, that's okay. We're going to spend a lot of time with these. We're going to come back to these over and over again. You're going to get intimately familiar with this little M symbol. But for now, just remember this. As the physical part gets smaller, you get more tolerance. Or if it's a hole, as the hole gets bigger, you get more tolerance because it makes it easier for other things to fit in it. Okay, least material condition. Now, this is the opposite. It's saying that the tolerance changes as you move away from the least material condition, which is either the smallest peg or the largest hole. We're wondering, well, why largest hole? Well, if you're looking at it, how do you get rid of material? You make that hole bigger. So the bigger the hole is, the less material there is. And once you reach the limits, within the tolerance values, then that is the least material condition because that's as much material as you can take away without the part failing. Now, what does this do? How is it helpful? I'm not going to go into that right now. We're going to spend a lot of time on that later. Just remember, least material condition is either the biggest hole or the smallest peg, okay? Biggest hole or the smallest peg. The biggest absence or the smallest physical part. That's what's going to help you. And it does have some amazing uses, but we're going to see that several chapters on from now when we start talking about position tolerances. So that'll be it for this time. Thank you all for listening. And I'll see you next time as we talk about our boundary conditions.